Good evening, everyone. Are you able to hear me?
Good
Okay,
evening,
thank you.
madam.
So I hope we are fine. So can someone pray for us? John, your microphone is unmuted. Are you going to pray for us? Yes, Aldrin.
Let us humble ourselves for prayer. Father Lord, I'd like to thank you for this day. I'd like to thank you for the gift of life. I'd like to request you that as we are going in for this lesson, you may enable us to understand whatever is going to be taught today, so that may be of good use to us. We glory be to you in the mighty name of the Son, our Lord.
Amen. Thank you, Aldrin. So today we are basically going to start from where we stopped. But maybe before we do that, there is a video I had wanted to share with us last time on radioactivity, but I wasn't able to, so probably we can watch that for now. Oh, but before we do that, I just wanted to share with us today's devotion. I was inspired to share it with us, so I hope you're blessed as you listen. So it says, Christ in you. Colossians chapter 1 verses 27 says, to them God willed to make known what are the riches of the glory of this mystery among the Gentiles, which is Christ in you, the hope of glory. David, Moses, Elijah, Deborah, and other great men and women in the Bible did mighty things for the Lord. Do you know why? It's because God's presence was with them. God's presence turned them from ordinary people to extraordinary persons. As God's child, you have something more precious than them all. Yes, you do. You have the Holy Spirit, not just with you, but inside you. Isn't that beautiful? Christ in you makes you 1,000 times bigger on the inside and a Superman. So go about your activities today joyfully, knowing that you're more than a man because Christ is in you. Hallelujah. So Christ lives in me through the Holy Spirit, and Christ in me is the hope of glory. Therefore, his glory is seen in my spirit, soul, and body. In Jesus' name, amen. Okay, thank you for listening. So I'll just share with us the video. It's just 4 minutes. So you listen in and then we can go ahead and try out some examples on Half-Life, then we can continue. No. Are we all not able to hear the volume of the video? Are we now able to get the sound of the video?
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta- decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta- decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any.
So are we able to hear the volume thereafter? So I'm going to replay the video once, but I wanted to know if we are able to get the sound. So the beta plus and the beta minus, we looked at it last time. We said a beta particle being lost, that is when we have the beta minus in his kind of explanation. And then the beta plus, we looked at it as the positron, where we have the electron capture factor. So it's more like the same thing, just different terminologies. And then probably there is something I wanted to correct. Last time when we saw the electron, the other side with a +1, that still remains as a positron because you're adding an electron to the molecule that is being lost or gained. So on whichever side it is, you just balance the atomic numbers to get the actual number of protons that was lost or gained. But of course, we are going to look at the nuclear stability graph, like he explained at the end, and we'll see how that works.
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of 2 neutrons and 2 protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta- decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta+ decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta- or beta+ decay.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any questions. Why not check out our FuseSchool app as well? Until next time.
Okay, so there's someone in the chat asking for a repeat in the beta plus and beta minus. Remember last time we looked at the different emissions that are being made. So the beta minus is basically showing the beta emission that we looked at. And then the beta plus is showing the positron where we talked about the electron capture kind of application, where you have the electron with the +1 instead of -1. So the beta plus is basically explaining the electron capture positron, which is the electron with a +1. And then the beta minus is explaining the emission of the beta, which is the -1 on the what? On the atomic number. I don't know if that adds up for now. Okay, so there are some numbers I had come up with for half-life. So I wanted us to try out at least 2 of them, then we can move on to something else. Because I remember last time we had tried out 1. So I want us to try out one of them, 2 of them, and then we can, the other one, you can try it out in your free time and we are able to move. So I hope all of us can see the screen. We have the half-life of phosphorus 32 is 14.26 days. Determine the percentage of the sample that remains after 35.0 days. So we have just 2 minutes to try out that number 1, then we can go through it. Or I can confirm the answer so that we move, because at least we had tried out some examples. So let's try out number 1 and number 2. Then number 3, you can try it out in your free time. If you get the answer, please feel free to post it in the chat so that we can quickly move. Okay, people trying out because I need to know what is going on. Okay, so I'm going to go over number one with us because since I'm not getting any feedback, I don't know if people are trying out or yeah, or they are also pausing like me. So what we are going to do, let me just try out number one. It says the half-life of phosphorus 32 is 14.26 days. Determine the percentage of the sample that remains after 36. So we have the half-life they've told us is 14 days. So that means RT a half is equal to 14.26 days. But then they have also told us to determine the percentage of the sample that remains after those days. So that means the time taken for the sample to decay is 35.0 days. And since the question is talking about percentage, that means the original mass, which we termed as N naught, is equal to 100%. So the question is asking for the percentage that remains after. So that means you are getting NT, which we do not know. So since we have our half-life, the other time we looked at the formula for half-life, we said half-life is equal to ln to lambda. So ln to lambda, we need to know what our decay constant is. So that means since we have the half-life, which is 14.26, is equal to ln 2, which actually we also said is 0.603 divided by the what? The decay constant. So that means our decay constant is going to be equal to 0.03 divided by 14.26. What is going to be our decay constant there? What answer do we get? Sorry?
Is it 03 or 93? It's 0693.
Oh, 06. Oh, thank you. So,
Yeah, 04. Let's take
not 0. There is no
0.693.
0. It's 0.693. Yes, thank you.
693.
So what answer do we get? After dividing with 14?
We get 0.048.
We get 0.048.
048.
0.8.
59.
59. So we can make that 6. And then remember we talked about the units since it's in days, so it becomes per day.
Yes.
So that is our decay constant. So after getting the decay constant, we denote the formula for calculating the what? The actual mass that was remaining. So that means we'll have ln of n naught over nt is equal to lambda t. So since we have this, and we have that, we can feed them into the formula. So that means we'll have ln over 100 divided by nt, which is equal to lambda, which is 0.0486 times our time, which is 35 days. So after getting that, if you can remember your logarithmic knowledge, whenever you had log of AB is equal to X, you would say A is equal to B of power X. So if we are to apply that here, when we make the ln to cross, because remember, we talked about ln having that association with the logarithm. So in most cases, we denote it as 100 over nt is equal to E of 0.0486 times 35. So the E is already there on your calculator. All you need to do is to just multiply the figure that is up here, pressing the E, pressing the figure, then it will give you the answer. So I'm going to rub this side so that at least I can use it. So that means we are going to have 100 over nt is equal to E. When you multiply this figure up, what does it give you? Anyone that is multiplying?
You get 1.701.
1.701, good. So when you press E on your calculator, it's where the ln is. So you press the shift, then the ln button, then you press in this figure. What does it give you?
It is giving me 5.47.
5.479. 479. So to get the value of nt, we are going to have 100 divided by 5.479. What is our nt?
It's lying.
47.86.
Sorry?
47.863.
47 point
863. 863.
So we can stop at that since it's a percentage.
Yes.
So that will be our percentage, our decay at NT. I'm seeing some people in the
Yes,
chat
so
saying
that's
we left them. Are you
yes.
sure you calculated well? Because my calculator is giving me a different answer from 47.
It's giving a different one.
Yes, because if I get 100 divided by 5.479, it's giving me something else.
Yes, me too, I'm getting 18.5.
Yes, so it's supposed to be
It's It's 18.25.
18.25%. So that is the mass
Yeah.
that remained after decay.
Yeah.
No, but even when you use log, it should be able to give you the same answer. Because if you use
Excuse
log,
me.
yes, please.
Using log, it's using log, like even though I've been running off, I'm getting 17.985.
17 point
985.
985.
5. Yeah.
So you realize that if you approximate this answer, it's going to give you 18%, right?
Yes.
And even the answer we've gotten here, if we are to approximate it, it will still give us what? 18%. So it's about you applying the right procedures to obtain those answers. As
So
long as
maybe
you've
if
used
I'm to use
Hmm?
if I'm to use log nt minus log n naught is equal to negative lambda t out of 2.303, it still gives the same.
Yes.
Okay. Yeah, it's once I used and it's giving that answer. So, but since we like if we approximate, it gives them.
Yeah, so it should be able to arrive at the same answer because much as you're using different applications, those applications should be able to give you the same approximated answer.
Yeah.
And if you
Okay,
realize
thank
that if
you.
you don't overround off, it will still give you the same answers, really. So the people that got lost, I don't know where we should pick you up, because if you attended last week's lesson, then you should be able to rhyme along with us. But I can just repeat briefly what we just did here. And if you still don't understand, please, you go and look for the video on YouTube and watch. So I said, after getting half-life, I'm going to start from half-life where I stopped. So we said calculating the mass, you get N naught over NT is equal to lambda T. And we've said our N naught, since they're talking about percentage in the question, is 100%. So that means any mass we are calculating should relate to a percentage. That means the original mass was 100%. So the NT is what we are looking for, the mass that decayed after 35 days. So that time was given to us, which is 35.0 days. Then, of course, we've calculated the lambda, and our lambda was 0.0486 per days, because we said this is very important. So after getting that, you just come and feed them into your formula. That is by getting ln of N naught, which is 100, divided by NT, which is equal to lambda T. No, I can fill in those values. So if our lambda is 0.0486 times the time, which is 35. So when you multiply this, it's going to give you ln over 100 over NT is equal to 1.701. So I said where there is ln, because we are applying logarithmic factors. As a math student, you may know that ln is the same as you expressing it as 3.030 log 10 of 100 over NT, which is equal to 1.701. Or alternatively, if you don't want to go into this subject of logarithms, ln crossing the equal sign takes on the format of an E because E is expressing this log of 10. So that means you will have 100 over NT is equal to E superscript of 1.0.71, which gives you 100 over NT, which is the same as you having 5.479. So when you cross multiply, obviously it's going to give you NT is equal to 100 divided by 5.479, which is the same as you have in your NT as 18.25%. So I hope that was able to help. Okay, so we also looked at number 2. Had we tried out number 2 or we go through it together? Okay, so let's first try out number 2 before I do it for us, because I want us to learn by doing things ourselves. Because if I do all of them, we might end up not attaining our objective for that day. So first try out number 2, and then we can try it out together like we've done for number 1. And you notice, at least if you try out, you know where the problem is when I am working out and you're able to ask for guidance. But if I try out and you didn't try out, then it becomes quite hard. So let's first try out number 2, and then we can try it out together. I'm giving us 2 minutes, so that means at 4:52, at 4:53, we'll be going through the number together. Yes, we say the decay constant must carry units at all times. So as you express it, you'll see the units coming through. So as you work out, make sure you include the units. Very, very important. Yes, ln 2 is a standard expression when you're dealing with radioactive decay. Okay, so our time is up. I want us to go through number 2. So it's telling us the half-life So it's telling us the half-life of a certain isotope is 20.4 years. So that means we've been given the half-life, which is 20.4, and then calculate the original mass of the sample. If it takes 100 years to decay, that means this is the time to decay to this mass. So that means this is our NT. So this time around, we have our NT, and they're asking us to find the original mass. So they are telling us find the original mass of that isotope. So what we are going to do here, first of all, is to find the what? The decay constant. So our decay constant, in this case, we have, remember we discussed about the formulae. T1/2 is equal to ln of 2 over lambda. So that means our T1/2 is equal to 0.693 divided by our lambda. Since we have that T1/2, we write it there, which is 20.4. So that means our lambda in this case is going to be lambda is equal to 0.693 divided by 20.4. So what is our lambda going to be? Those who worked out, what lambda did we get? 0.03.
0.397.
97.
Yeah.
So that means we have our lambda as that. Is there another 3 after the first 3?
Yes, there are 2 threes.
So we have 397, of which we can say our lambda is the same as having 0.034 per year, since the time was given to us in years. So that is per year. So that is going to be our lambda. Then of course we'll go on and show our expression of the masses N naught over NT is equal to lambda T. So we have our NT, we have our lambda, we have our time. So that means you're going to have ln of N naught divided by our reduced mass, which was 27.25, is equal to our lambda, which is 0.034 times 102 years. So our ln of N naught divided by 27.25 is equal to, what do we get after multiplying?
3.465.
3.465.
465.
It's 8.
It's 8.
Yeah.
Okay, thank you. So after getting that, we introduce the E, which is going to give us, I hope you're able to follow, because let me just rub this side, because screen seems small for the calculation. So that means I'm going to have N naught divided by 27.25 is equal to E of 3.468. So that means my N naught is over 27.25 is going to give me, what do I get? Hmm.
94.2250.
What does it give you?
94.2250.
94.2250. So to get N naught, that means I'm going to multiply this times this. And what does that give me?
No, that is after multiplying.
After multiplying, no, I wanted what you get when you have e power 3 of 34. So this is, I'm getting on my calculator 32.073. So after getting that, I have, I don't know whose Gundi that is. It's producing a lot of feedback. So we have 32.073 times 27.25. So if I get 32.073 times 27.25, this is going to give me my N naught is equal to 873.99 grams. So I don't know if that is what we got. Or if you're to write with 3 decimal places, it would be N naught is equal to 873.989 grams. And that will be your answer.
Yeah.
Okay, so I'm glad at least some people got that. Okay,
Yes.
let me see what the response in the chat is. Okay, so basically that is what we have for that number. So I don't know if we had popped number 3. If you hadn't, please just take a screenshot because we are not going to go through it since it's already 11. Sorry, it's already 17 hours. We need to move on to something else. And I think at least now the concept has arrived home. Because the most important thing is to get the concept. And if you get the concept, try out numbers in the QB so that you're able to be conversant with the what? With the terms that we are using. So I'm going to just, yes, please.
Mom, how are we using the if? When I put it on my colleague, they are giving me syntax error.
No, just
No,
press
you first
shift lean,
shift.
then feed in the number.
Yes.
Oh, the lean.
Press
Shift
lean,
then
then feed in the number.
Okay. Thanks.
Lindsay, just try out with logarithms and then you can share the concept with us and then we can guide from there. But otherwise, the E is a much easier alternative because at least if you know that if I had log 10 and I take the figures up like you do in logarithm, it becomes easy for you to manipulate that, that equation. So it's the same thing if you had 2.303 log 10 of n naught over nt, giving you lambda t. So that means in this case, you are going to have 2.303 n naught over nt, giving you 10 power nt of that. Then, of course, you're able to substitute mathematically on how to go about that. So I hope that makes sense. But now if you had just ln here and you just crossed over, for example, if I did this of, so I'm writing here because I want us to screenshot that number 3, then we move on to something else. So we have, if I had ln of nt over, sorry, n naught over nt is equal to lambda t. That means where this ln is, the e comes in as an exponential of that logarithmic term. So that is why I have n naught over nt is equal to the exponential of lambda t. So it is just an exponential to express the ln. That is why you find that even in your calculator, for you to get the e, you press shift of ln, because it is an expression of the logarithmic term in the ln terminology. So I hope at least I've tried to break that down for you, Lindsay.
Yes, thank you, teacher.
All right. So someone is asking how they can join the help lessons. I think this is our last lesson this holiday. But of course, if you're on the WhatsApp groups, you always receive those notifications on when lessons are beginning, and the timetables are posted on those WhatsApp groups. And then the other thing, if you miss our lesson, since we can't go over a lesson that was 2 hours last week, you go to the Holistic e-learning platform YouTube page. Those lessons are always posted. And in most cases, in the evenings, if you check, Mr. Kazvores posts the links to the YouTube channel of the lessons we've had that day. So you can always go back and review. Okay, so we've been looking at half-life. So I want us to look at a graph that represents the half-life concentration against the what? Against the time. So when we are dealing with half-life graphs, of course, I'm going to give us some examples to try out. We'll just try out one example because of time. So the rest you'll try them out later. So we have a graph of NT against time. So this time the NT we are looking at is in relation to the half-life graph. Because when you're drawing the half-life graphs, like we will see the values, the concentrations depend on the time. So if we have half-life, that means the original concentration was halved. So that means it will happen at T1/2. Then if the T1/2 we've obtained, the concentration we got is still halved. That means still we will get the concentration at T1/4, because as time increases in halves, the concentration also reduces in halves. So that means if I had my graph, for example, as this, and this was my time in seconds, and this was my concentration in moles per liter, that means I would have my graph in this kind of shape. As you draw them, you're going to see the kind of shape they'll give you. So if this was my NT originally, and my NT is halved, that means this NT being halved occurs at half-life. Because remember, we said the original mass is halved for us to obtain the half-life. So my lines may not be very straight, but just follow through. So we have T1/2. So then if this mass is halved again, you will have NT1/4, because you've halved that mass again. And that will happen at T1/4. But this will become NT1/4. Then you'll move on to the next. If it's halved again, I expect that it has t 1 over 8. And this will become
Yes.
nt over 8.
Out of
Are we together?
yes.
So the more you have the masses, the more the time also increases in halves. So that means at nt over 2, you'll have your t as a half. At nt, because remember, now you're reducing the mass. As you reduce the mass, obviously the time is what? Is also increasing, because the mass reduces with increasing time to gain a more stable substance. So half-life will just keep on increasing as you reduce the masses, depending on what masses you're operating with. So when you're drawing that curve, it should be in that kind of relationship. So that is basically how you can represent the half-life graph in relation to the initial concentration and the time taken. So when you get to kinematics, you will learn about the first order, second order equations. So since we are looking at half-life, half-life becomes a first order reaction, because for you to get the differences in time, for example, t a half, because this was initially 0 time. So t a half minus 0 is equal to me having t a quarter minus t a half is equal to t a eighth minus t a quarter. So depending on how many times you will have generated, that is how you will be able to obtain the different times that were taken. And the values are the same from time a half to 0, from time a quarter to time a half, from time 8 to time a quarter. So the time differences within those different phases are the same. So basically, that is the information you really need to generate from those graphs. So if we are together, I want us to note down this question and you try it out and we see what we get. Are we ready?
Yeah, ma'am.
So it says, the table below shows how the activity of iodine hyphen, there is a dash there, a small dash, 128 varies with time. What I mean is this: iodine dash 128 varies with time. So I hope at least you have a graph paper, because this is going to require you to draw it on a graph paper to get information that is accurate. So you have your table, and the first row has time in seconds. And then the next one has activity. That activity is in counts per second. So the first, you have 0, 190. Next table, you have 500, 146. The next one, you have 2000, 75. The next one, you have 3000. $45. The next one you have 4,000, 27. The next one you have 6,000, 10. The last one you have 8,000, 4. So part A says, plot the graph of activity against time. Plot the graph of activity against time. Then part B, use the graph to determine the half-life of iodine 128. Use the graph to determine the half-life of iodine 125. Use your graph to determine the half-life of iodine 125. Sorry, 128. Then the last question is determine the decay constant for iodine 128. The person asking for pardon, I think I drew the table here, so you can copy the values from the table. So we have part C, determine the decay constant for iodine 128. Determine the decay constant for iodine 128. The one who is very lost, I don't know where you're lost and why you're lost, because this is an example that we are going to try out on a graph paper. 128 stands for the what? What should I say?
The mass number.
Yes, thank you. So it stands for the mass number. The first question is plot the graph. The second question is determine the half-life. The third question is determine the decay constant. So the table is for you to use it to plot the graph of activity against time. After plotting, I expect us to determine the half-life. Then because we have the half-life and we know the formula for half-life, we can calculate the decay constant. So the main concept I want us to get here is how to read off half-life from the graph. That is by interest on this number. So please, let's try it out very fast and we see what we get. So how do you expect to get the answers without drawing the graph? Obviously, you're drawing the graph, my dear. Because you can't get the what? The slope without knowing, without plotting the graph. You need to plot the graph, obtain the slope, use the slope to find the half-life. That is why I want us to draw the graph so that we share what we are supposed to do. So as we go through those numbers, let me just try to put down these numbers that I want us to try out later on, so that you just take a screenshot. Yes, please, it is. For this holiday, really. But Patience, I think I gave you the questions. I gave you 2 questions. So after drawing the graph, find the half-life, then use the half-life to find the what? The decay constant. I think I gave you the next questions. Okay, so someone is asking, do we use a ruler? So every time they tell you plot this against the other, the one that comes first goes on the y-axis, then the one you're plotting against goes on the x-axis. So for example, the first one was asking you to plot the activity against time. So that means you plot activity on the y-axis and time on the x-axis. So someone is asking, do we use a ruler or freehand? So it depends on the kind of graph you've obtained. What kind of graph is it? Is it a slope or a curve? Because if it's a slope, you use a ruler. If it's a curve, you use a freehand. So Diana, what kind of graph have you obtained? A slope or a curve?
I'm repeating the graph. I'm not understanding it.
How? Did you use a correct scale?
Like to
That's what I'm trying to
inquire
figure out.
I would like to inquire the one in the second column in the table. Which value was in the second column for the side of activity?
146, the one under 500
Yes.
was
Okay,
146.
thank you.
Okay.
Thank you. Then the first one?
The first one was 190.
Okay, thank you.
All right. So someone is asking, how do you determine half-life after drawing the graph? Remember, you're looking at these activities. So what you're going to do, remember we said the different half-lives we obtain should have an equivalence, like they're equivalent to each other. So what happens is first ask yourself, what is half-life? So what was the original mass? So if I have that original mass, what activity do I get? After getting the activity at that point, for example, I can just illustrate here because personally I can't draw the graph for now. So what happens is, just a minute, let me first save this. So if I was to come back to my slide here and I drew my graph, remember we said this can be NT. So if I have my half-life is obtained by NT divided by 2. So if my NT was 190, what is 190 divided by 2? If I get the
90.
value here, sorry?
95.
95. So if I get my mass as 95, I will come to my scale and look for where 95 is. Because remember, I expect your graph to at least have something like this. So if I have that curve, I'm going to come and look for where 95 is. So where 95 is, I'm going to, you remember how you used to read off frequency Is it cumulative frequency where you read off the median and things? So you will come and read off, you dot from 95 to where the curve, to where 95 reaches that curve, and then you drop with dotted lines. After dropping, you draw an arrow there. Because now this one is reading as time, so you will have your time there. Are you getting my point? Then like the other side where we did the half-life curves, if I got 95 divided by 2, what will it give me?
We have 47.5.
47.5. Good. So if I have 47.5 and I came to my graph and I read off 47.5, what kind of time will it give me? So that differences within those different timings. But now this is just like a general formula. If I know what my original mass was, because remember my NT gives me the original mass, and that original mass has not yet decayed. That's why you see its time is 0. So if it is the original mass and I half it, then I drop down. That gives me my T1/2. So I hope at least I've tried to explain that bit. So after that, you please find the decay constant using the formula of T1/2 is equal to lambda, sorry, ln 2 over lambda. And because you've used different scales, your what? Still your answers at least should be close to each other, not someone getting an answer that is far different from everyone else. So your answer should be within the same range.
Excuse me, ma'am.
Yes, please.
Ma'am, I'm still confused. What is the decay constant?
Can you remove the word confused and ask the question?
I mean, what is the decay constant?
So remember, when we are looking at radioactivity, you're looking at what? At the spontaneous disintegration. That means there is decay happening in that disintegration, right?
Yeah.
And if it is happening, you have what we call the original or initial mass, and then you also have the what? The mass after time t. So that decay constant comes in as, because I didn't explain these formulas because we've not yet studied integration in math. So it will give me a lot of work for me to go into that math. But of course, I told the people in the first lesson, if you were around, that decay constant is generated as a result of those small changes that occur during the disintegration process. So that is why you'll find that when you're calculating the formula for the decay masses, you realize that it comes from integration, but since you've not yet done integration in math, and since the extraction of that formula or the generation of that formula is not really key in chemistry, that is why I left it out. But I told people who wanted it on a personal level to either read or consult. So it is up to you, but the decay constant is generated as a result of those small changes that occur during the disintegration process.
Yes, the end.
Okay, so at least I can see someone came up with the answers in the chat. Patience, that is good, but please put units on your answers. Otherwise, it may cost you, yet you've gone through a lot of work to get there. So for half-life, you will have seconds, since our time was given to us in seconds, 1/400 seconds. Then for the decay constant, you will have per second, which is written as per second.
It's second power -1.
Yes. Mikova, what scale did you use? Because that value seems to be very big, far from the most correct value. Okay, right. It seems to be very far.
Mom, I used 1,000.
1,000. Why is it that wide? Looks far wider. But I hope you've operated with the right principles, because it should be able to give you the correct answer.
Yes.
So Sun is asking, how do we get the decay constant using the graph? You can obtain the decay constant from a graph that is represented by a slope. For example, the activity I'm going to give you to try out outside this lesson, you're going to notice that you need to generate a slope. How you use to calculate the gradient in math is the same way you're going to calculate that slope. That slope is going to give you the decay constant that you are looking for. So after getting the slope, in that case, you will have, but I hope people understood the half-life thing here, because now if I'm explaining that one, I need to rub here so that I use this place.
Yes, Mom.
So the example I've given you down here, I'll show it after explaining this. For example, for it, you're going to obtain a slope kind of graph. So you're going to have this. This is what I mean by a slope. So if I have this slope, the same way you used to obtain gradient in math with change in y over change in x is the same thing you're going to do here. You're going to pick two values on that line. Of course, you draw a line of best fit where most of the values are covered. So you will choose a point here and another point there. Then, of course, you will have an x value and a y value. And then you will have another x value and y value here. Then you will obtain the slope as equal to change in y over change in x. I hope you remember your math very well. So you will have y2 minus y1 over x2 minus x1. And then you will obtain your slope. In this case, your slope will more like act as that t a half. So that means you'll go back to your formula and say t a half is equal to negative lambda over the 2.303. Sorry, 2.903.
It is 303.
Yeah, 2.303. So that means I'll have t a half is equal to, so what I got here as my slope value is what I'll come and feed here. The slope value will be here is equal to negative lambda over 2.30. And then, of course, you will get the value of your lambda plus the units. So that is how basically you can generate your lambda from the graph. But still remember, even here on this number which you've just done, you used the t you got from the graph. So in that case, you're basically calculating using the graph to get your lambda.
Excuse me.
Yes, please.
Now, after getting, is it right for me that after I've calculated the half-life, like after I've read the half-life from the graph, to use the formula of the decay constant equal to 0.693 out of half-life?
If you've used the
if I have got the half-life from my graph, and then I want to find the decay constant, is it right for me to use 0.693 out of the half-life?
Yes, that is what you're going to use on this graph that I first gave you here. Okay, I think, let me just re-explain this again. So here, on the graph that you got at first, the one that you've been trying, you realize you obtained a curve, right? So after reading off from 95, and you read off the half-life, because that is supposed to be a dotted line. That means for you to get your lambda, you're going to have to write T a half is equal to ln of 2 over lambda. So you have this, you get this. Are you getting my point? I don't know who asked, but I hope the person understood. Then there are instances where we have, because remember the question comes in different phases. So if I have log of activity, log 10 of the activity against time, this is more like me plotting my graph of log of nt. If I had log of n and then time here in maybe seconds. So my graph may appear, depending on the examples you're given, it may appear as coming down here, coming from up as a slope going down. So if my slope is facing down, that means it's a negative slope. So definitely my slope will be in negative terminologies. So that means I'll have my difference, my change in x and my change in y. So still here, my slope will be related to slope is equal to negative lambda, because the slope is negative. It's going to the negative direction. So it is negative point because of the logarithm. It comes with a 2.303. So that is how you obtain your slope for a negative slope. The lambda is negative. But if I had a positive slope, for example, if I had log of n naught over nt, the slope would be different. In this case, the slope would be coming from down going up. So over against time, that means my slope is a positive slope because it's going to the positive direction. That means here my slope will be equal to positive lambda over 2.303. So you have to take note of what kind of graph you have, and then of course you relate accordingly. So that means here I have my change in x and then my change in y. So like I said, you just choose 2 points from that graph. They may not be points that were given to you in the table, but as long as they fall on that gradient line, you can use them to find the what? The slope. So after finding the slope, we know how we get the slope. The slope is equal to change in y over change in x. Then if you're getting your half-life, you just feed them into that formula, and they're able to give you the different measurements that you are looking for. So all these things I'm explaining come from the kind of graph they have told you to plot, because sometimes they'll give you activity against time, and then they'll tell you plot the graph of log activity against time. So if you get the logarithms, because I know you did those things in physics where they give you maybe a value of x, and then they tell you plot log x against time. and then you need to calculate the logarithm of x, and then you plot it against time. So it's the same thing here. If they're giving you activity n, and then they tell you plot the activity, the graph of log of activity against time, you're going to first find the log of that activity, then you plot against time. And then, of course, the graph that you get will be able to direct what formula you use. So the formula is the same. The only difference is when you're getting the slope for that curve, for the slope that is facing down, because it's going to the negative direction, the lambda becomes negative. And because this side, the slope is going to the positive, because it's log n naught over nt. So here they have given you values of nt over n naught. So if you get their logarithm, the value will be going up. The values will be increasing in the positive direction. So because they are moving to the positive, the slope, of course, that you will obtain on your graph will be positive. That means the lambda will be positive. So after getting the value of the slope, you have this value. It's going to help you get the decay constant, which is lambda. So I hope I am making some sense through that explanation. Okay, so the rest who are not responding, I hope we are trying to take in these things. I should have given you these graphs before giving you that activity, but thank God, at least when you tried out that occurred that I really had to give you those things. So you expect 3 graphs. You expect the one for half-life, which is curve-like. Then you expect one with a negative slope, and you expect one with a positive slope. So you just have to read them, because I don't expect you to digest everything at the word go. Though there are those people who can digest everything as it comes. But if you feel it's too much to take in, after the lesson, take some time to cool off and go back and review what you've written. And also, you can also play the recording in case they posted the link or you find it on YouTube. Because when you subscribe to the holistic YouTube page, it will always notify you when new videos have been uploaded. Because me, I always get those notifications. So it's important that you try out or get someone to re-explain for you. It will make things much easier. Okay, so I want to move to this slide so that you can take a screenshot of this number that you will try out later on. So I hope it's okay for me to rub off these things because they will keep displaying in the question. So is it okay for me to erase them?
Yes.
Okay, thank you. But I hope at least you've written down those things. They are important for you to know, especially for paper 2 where they can tell you to plot the graph. So since you're not in the mind of the examiner, you may never know which graph the examiner has chosen to bring. So let's just take a screenshot of this question and we'll try it out. And please always remember the units. The units are very, very important, very, very key. So please always remember to include them. So if you're through, please let me know so that we move.
We are done. Of course. We are done.
Okay, good.
You're done.
Okay, so I want us to also look at what we call artificial radioactivity. I don't know whose mic is unmuted, but it's producing sound. So, what do we know about artificial radioactivity? Anyone who has an idea? Akram?
Okay, madam. Artificial radioactivity is the spontaneous disintegration of the unstable nucleus to those below, to those of above of bismuth, element bismuth.
Okay, thank you. Okay, I can see the chart is when a nucleus is forced to decay by application of physical conditions like temperature. Okay, that's interesting. So the same way you hear artificial radioactivity, that means it involves the application of man for these things to actually disintegrate. So when we are looking at artificial radioactivity, we look at two instances where we have combining of nuclei and then also splitting of what? Of nuclei. But as these things happen, you're bombarding stable nuclei with an artificially made radioactive substance. So for example, when we are looking at artificial radioactivity, we look at two things. The first one is nuclear fusion. And then we also have nuclear fission. So, what do we think about nuclear fission? What is nuclear fission?
Nuclear fission is when two lighter nuclei join to form a heavier nucleus.
Okay, thank you. That is good. Anyone else to build on that? Because there is something that she just needs to add to that statement, but otherwise it's a good to go answer. But what can we add to it to make it actually nuclear? Anyone? So the same way you hear the word fusion, that means things are coming together. And because it's nuclear, that means nuclei. And because we say disintegration involves unstable nuclei, which is heavy. So it means in this case, fission requires two lighter nuclei. Two or more, they can be more than two. So we have light nuclei combining to form heavy nuclei accompanied with release of a lot of energy or large quantities of energy. So when these processes are taking place, we expect the energy to be a lot, like a lot of energy. So that statement should be included there, accompanied by release of large quantities of energy. And then when we come to fission, of course, we are going to look at the examples, but I want us to first define these. What about fission? What is nuclear fission? Then are you defining fusion or fission? Because I'm seeing fusion with you, yet those are two different things. Yes, Techno? I don't seem to hear you. Okay, I can't hear you, but when we are looking at fission, fission is the splitting of heavy nuclei into lighter nuclei accompanied by large release of energy. So here you're splitting the heavy nuclei into a lighter one or into lighter ones, but with release of energy. So all these processes are taking place with release of energy. That means as we write the equations, we should add the energy there because it's a big product that is given off at the end of the day. So that means even in your definitions, you need to include that loss of energy there. So Sally is defining artificial radioactivity can also involve bombarding stable with appropriate atomic projectile to form unstable nuclei. Okay, good. So we have some examples here. You're going to tell me if it falls under nuclear fission or fusion. We're going to just write some equations here. So you will tell me where they fall. How to H plus 3 H equal to we have A, B, and then we have C. 22, 36, they are plus 1, 1, 56, equal plus 3, 4, 3, plus 2. So which equation among these three falls under nuclear fission? After looking at those definitions, which of these three fall under nuclear fission? Fission with Fi.
The third one.
It's the third.
C.
The third one.
The third one, okay. C. So this part C is what falls under fission because we've said it's the splitting of a heavy nucleus to form lighter lighter nuclei with release of a lot of energy. So you realize that here the uranium splits to give us this and that, and this, and then the energy that is given off. And then these two fall under, obviously, nuclear fusion. Fusion is single S. So here you realize that we are bombarding two nuclei to form a heavier one compared to these other ones. So basically, that is it about artificial radioactivity. So of course, time may not allow us, but I want us to go back and read about nuclear stability. I don't know if we will be able to have another lesson next week. If we do, because I would love us to share together about nuclear stability. But if we don't, still your teachers will cover it at school. So just go ahead and read about it, and so that if we have the lesson, we can interact together to tackle that. But otherwise, please try out that graph number, look for more numbers in the question bank and try them out. Because every time you try out these numbers,
Excuse me,
it
what
gives
is
you a
excuse me,
better
what is
view.
the other topic? You have said it's called what?
Sorry?
You have said the other topic is called what?
It's not a topic, it's a subtopic because it's under radioactivity, nuclear stability.
Nuclear stability. That one we already studied it.
Okay, so for you did, but the rest I wonder if they studied it. So
Oh, okay.
so that means you had done radioactivity, right?
Yeah, we're rest on the stability belt.
Oh, that was cool. So that means you are even about to finish. Because if you're looking at nuclear stability, you're looking at the factors that affect stability of the nucleus.
Yes.
And the stability belt is one of those things that you look at amongst the other factors. So the rest of us, we can go ahead and read about that and we see how we can interact if we are to have the lesson. If we don't, then at least you've learned something from these 2 days that we've made.
Yes, I'm really grateful for that because I've really learned something.
Okay, that is very interesting. Thank you for that feedback. It's a good one. Okay, so like I said, if you have not been able to understand what we've studied from last week's lesson, please go to the YouTube channel for Holistic and look, at least it's the only holistic e-learning platform on YouTube. Subscribe so that every time your class has a lesson, YouTube notifies you and you're able to go and watch. And there is no investment that is too expensive if it's adding value to your life. So please go ahead. I'm seeing a lot of thank yous in the chat. Thank you everyone for being patient because these hours are hours where people usually sign out, but thank you for attending the lessons. So thank you everyone and have a lovely evening.
Thank you.
Akram, it may be hard for me to note down your number, so maybe just note down my number. You will just inbox me and then I can see how to get the work to you.
Okay.
Yes, otherwise, thank you and bye.